Welcome to Calculus AB video for skill number 123. I can use infinite limits to explain asymptotic behavior. And featured to the left we have a sculpted female figure serving as a sculpture. And the question for the video is, what is the term for columns that are carved in the shape of female figures? Right. In this lesson we're going to be talking about taking the limit as x goes to infinity, or infinite limits. And very straightforward, the limit as x goes to infinity of x goes to infinity. And you can think about that if you've got the graph of x. As we go further and further to the right, we're going further and further up. Same as if we did the same for x squared, that goes to infinity, or x to the third goes to infinity, etc. So if we wanted to find the limit as x goes to infinity of a function, we could actually split it into the limit of x squared and the limit of 5x. And in this case, the limit as x goes to infinity of x squared is infinity, and the limit as x goes to infinity of 5x is infinity. And we do that by direct substitution. And obviously infinity plus infinity is infinity. Now in the second one, what we've got here is the same scenario, except in the difference is we're taking the subtraction. So we split 3x to the 9th and negative 25x to the 8th, and we get this infinity minus infinity. Oh noes, which infinity is the bigger infinity? We can actually conclude that the higher powered infinity, the higher powered one, is eventually going to grow faster than the lower powered one. And for proof of that, you don't need to look too far. You can just take a look at the graphs. There's x squared and x to the third and x to the fourth, and eventually each power grows faster and faster. So at some point 3x to the 9th will outgrow 25x to the 8th, and so this first infinity is larger. So our first infinity subtracting our slightly smaller infinity will still yield a net result of positive infinity. So the answer here is equals infinity, because this one is small. I know that's kind of a weird concept, a large infinity versus a small infinity, but it actually does exist. So if this is the case, it would appear that we only need the highest powers of polynomials. The rest of it actually doesn't really matter in the long run. So here's our conclusion for the last problem. This note is kind of misplaced. I would encourage you to maybe apply the note after example 1. So example 1, we're taking a look at the limit of, we have the quotient of two polynomials. So we're only interested in the leading terms of the polynomials. So if we take the leading terms of the polynomials, we can rewrite the whole limit as just our leading terms. And we see that x squared over x, one of the x is canceled, and we're eventually taking the limit of this, which gives us infinity over 3 by direct substitution. So that gives us an answer of 3. Now we've got this this note here. If we take the limit as x goes to infinity of 1 over x, what we're really saying is 1 divided by a very large number. So the bigger that number gets, the closer this fraction gets to 0. So that's where we find that the limit as x goes to infinity of 1 over x is 0. and we're going to apply that in our example number 2. We want to take the limit, and the same rule applies. We're just interested in the leading terms because the rest of them eventually get outweighed. So we can take the limit of our function and just write it as the limit of the leading terms. And when we cancel that out, the x to the 7th and the x to the 8th canceled, and we're left with negative 2 over x. And the same principle applies. As x gets very, very, very large, this whole function approaches 0.
To infinity and beyond!
Alright, in example 3, what we've done is we've thrown in a square root in there, and again, I've put in a note that kind of feels misplaced, being a little slacker on my note making today. We already established that the limit as x goes to 0 of sine x over x is equal to 1. We can take a similar approach of sine x as x goes to infinity of sine x over x, and that equals 0. If we wanted to do a side exploration, we could actually use the sandwich theorem to prove this to be true. Perhaps we'll do that in class. Anyway, moving back to example 3, what we have is the square root of 4r squared plus 4 all over 3r minus 7. And we can take the similar approach where we're interested only in the leading terms. So if we take this and we isolate the leading terms, the leading term of our numerator is root 4r squared, and the leading term of our denominator is 3 over r. If we simplify the top, we get 2r, and the bottom simplifies to 3r, and those r's cancel, and that gives us a limit of 2/3, which means for our graph, as we go out to infinity, we're approaching a horizontal asymptote at 2/3. Example 4, we're going to do the same process. This time we're actually approaching negative infinity, so we're interested in what's going on as we go way out to the left. We can use the same approach that we have all along, where we take the leading terms, and in this case our leading terms are 2x and root 6x squared. So we take the limit of the leading terms, and when we are simplifying this out, we can pull the x squared out of the denominator, but it's important that we write it as negative x, because remember, the square root of x squared is actually equal to the absolute value of x. And so we have two scenarios. We have equals x if x is greater than 0, equals negative x if x is less than 0. So because we're approaching negative infinity, we're interested in the negative case. So we make that x equal to negative x. A sticky detail for sure. Anyways, the x's will cancel, and we wind up having 2 over negative root x. And there we go. There is our solution. I've looked through the worksheet, and I feel like these examples should be sufficient to get you through it. Usually direct substitution will spit out an answer for you. If it doesn't, try taking the leading terms and simplifying the leading terms, as we've done in the case of examples 1, 2, 3, and 4. Alright, thanks for watching the video, And the column to the left is called a caryatid. That is Caryatid. Caryatid. Female figure sculptures as a column.